the last hour of Physics 1C for March 8th. And we're going to do some problems where we can apply these kinematic equations. And this is the first one. A car goes from 0 to 50 meters per second for 20 seconds, and then it travels at constant speed for 40 seconds, and then it stops in 10 seconds. And it says to plot v versus t, and then find the total distance traveled. Okay. And the hint is to use the area under the curve. So there's two different ways you can do this. One way is to break this motion up into a bunch of little pieces and apply the kinematic equations. Or you can do what they say, plot v versus t, and then use the area under the curve. So let's do that. So let's make a plot. Like that. So it says a car goes from 0 to 50 meters per second for 20 seconds. We're plotting velocity versus time. And then it travels at a constant speed for 40 seconds. So we need to go from... The time needs to go up to about 70 or so seconds, right? Because it goes... It's 20 seconds plus 40 seconds plus 10 seconds. And the velocity, the maximum velocity is 50. So, yeah, let's try to do this. Everything's going to be straight lines because this is going to be constant acceleration. So let's mark off something. Yeah, it looks like we only need one indication for the speed. So let's say that this right here is 50. And we'll say that our velocities are measured in meters per second. Our times will be measured in seconds. That way we don't have to actually write them on the axes. We do need to have kind of 10 meters per second, or 10 seconds marked off everywhere on the bottom. So let's make a line, and we'll call this our 10-second kind of ruler. And I'll try to use it to measure off 10 seconds along this line. So that'll be the first tick. So that's 10. This is 20. There's a ruler that comes with this application, but from everything that I found, it only works on the touch version for some reason. It'd be really nice to have a ruler right here. So this will be 30. Wait, why did I do that? I don't know. I suppose if I use two different colors, I could probably just start marking them off more quickly, maybe. 2 at a time. Okay, so this was going to be 40, 50. I'm really regretting not doing this during the break. Oops. Just need to move this one over. If I can click this one. Click it. There we go. Move this one over to here. That should be all we need. This should be 60 and then 70. Should cover everything we need, but if it doesn't, that's fine because we'll have these two little measurements we can use. Like this. There we go. All right, let's draw a smooth curve on here now. Okay, goes to from 0 to 50 for 20 seconds. So we just need to go from 0, which is here, up to 50. And in fact, let's draw a line to represent 50 here because we're going to need to be able to see what that looks like because I can't. There's no grid lines here. So that's 50. All right, so this line needs to go from 0 to 50, and it needs to line up right here with 20. So I need to basically go straight up right here as much as I can. All right, there we go. That looks straight, right? Boy, it's really hard to tell. All right, so that's 0 to 50 for 20 seconds. It then travels at a constant speed for 40 seconds. So we need a red line that goes for 40 seconds, so from 20 up to 60, right? Right about there. And then it stops in 10 seconds. So my last line needs to just come from 60 seconds straight down to here. So it stops. So that is our curve. And we want to calculate So that's our velocity versus time. It speeds up, moves at a constant speed, and then it slows down. I think we can get rid of this line here too now. So the thing about this that I didn't mention before, but we can kind of use this problem as a way to talk about it, is we said before that the velocity of an object, Vx, was equal to, like, the instantaneous velocity is equal to basically dx over dt, right? What you can do is you can kind of rearrange the equation like this. You can split up your differential here so that it becomes Vx times dt. And then what you can do is this is equal to dx. And now what you can do is you can integrate both sides. And on the right-hand side, you're going to go from some x initial to some x final. What happens if you just integrate dx? What do you get? If I just write integral dx, what's that equal to? Just equal to x, right? Of course, you need to evaluate it between your limits. So this whole thing on the right-hand side is basically just going to become the displacement, right? Delta x. Yeah, x plus c, that's right, Chris, except if you have limits like these, then it's just going to be x final minus x initial, which we usually write as delta x. And on the left-hand side, you just need to put some limits in. So if you go from t initial to t final, you integrate your x velocity with respect to dt, then that's going to give you delta x right there. Or, in the language of calculus, we know that when you do an integral, right, that's equivalent to doing what? Taking the derivative is finding the slope of a tangent line, and yeah, taking an integral, this thing gives you the area under the curve. Now I know that, 190 is a class that is taken concurrently with this class, and that's something we're trying to change, honestly, but if you haven't studied integrals, I would suggest you maybe go read something about them, but if this is something you've never seen before, then maybe you flip ahead in your calculus textbook and kind of look at the introduction on integrals. Yeah, thank you, Kelvin. So it's in chapter 5. You all can teach yourselves at this point in time, and you just need to know in general what an integral is. You don't need to be able to solve complicated integrals in this class at all. You just need to understand this idea that the problem the integral is trying to solve is how do you find the area under the curve, and that's it. The other part of it is it's the opposite of a derivative. But anyway, okay, so that means we can just take the area under this curve. And this is a trapezoid, right? It's a trapezoid. You've got two parallel lines, and one line has a length of what? 20 to 60. This side is 40 seconds, right? The other side over here is 70 seconds, obviously. You can see that. And then the other thing, what's the other piece you need? You need two bases to do it an area. See, someone's putting in the chat. You also need to multiply by the height, right? And then you divide by 2. So our height, in this case, is going to be 50 meters per second. So the area, which happens to be equal to, in this case, the displacement or the distance traveled, because it's only going forwards, right, is going to be equal to the sum of the bases. So 70 seconds plus 40 seconds. You do a kind of average of the bases. You divide by 2. And then you multiply that by the height, which is 50 meters per second. And you end up getting, let's see, what is this? 110 over 2 would be 55. 55 times 50. 50 times 5, what is it? It's 2750. Okay, thank you. Appreciate that. I believe this works even if the object had been traveling in the negative direction, too. So, even if this object if we continued forward and the object basically started to go in the negative x direction, then you would get negative area, and that would indicate that it turned around, basically, right? So there you go. That's also equal to the distance traveled. Now, if we wanted something more than displacement, like if we want distance traveled, if it went in the negative direction, we'd actually have to add all the areas, but that's a different story. Yes, what's your question, Andrew?
Wait, so we did not just what you just did right now. We didn't find the area under the curve, did we? Because what I did was basically just I kind of cut the graph into three parts, three
Sure.
different areas,
You can do that.
and
Triangle
so
over
this
here, triangle over here,
yeah,
plus a rectangle.
and exactly, and then
You'll
I
get
got
you get the same answer, right?
no, unfortunately, unless I did something wrong.
Okay, so the area of the triangle on the left-hand side over here would be, this one would be 50, I'm not going to use the units now just to make this faster, 50 times 20 over 2, plus the rectangle in the middle is 20 by 40, right? Yeah. So 20 times 40, plus the rectangle on the right over here would be 10 times the height, which is 50 divided by 2. So this is 50 times 20 is 1,000 divided by 2 is 500. Plus 20 times 40 would be 800. Wait. 50 times 40. This should be 50 times 40. Yeah, I was like, this isn't going to work if I do it like that. Oh, I looked at the 20 here. I'm so sorry. This should be 50 times 40. The rectangle, to be really clear what we're doing here, the rectangle here has a height of 50 and a length of 40. Sorry about that. So 50 times 40 is going to be 2,000. And then 10 times 50 is 500 over 2, which is 250. And yeah, that gives you the same answer, right? So maybe you missed, maybe one of the numbers you did here was wrong or something, Andrew, but does that make sense? Math was wrong. Okay. Cool.
Mr. Horta?
Yes.
Why do we find the integral, like the Vx dt, and then we use another equation?
Oh. The integral is the same thing as finding the area, right?
Yeah.
So you would use the integral if you really wanted to, if you had an equation for the line. Okay. Let me give you an example. Okay. So what if I gave you the velocity and I told you your velocity was equal to, like, an object in free fall, 10 meters per second squared times t. Let's say that was my velocity, right? What does that look like? Well, the velocity as a function of time would just be a curve like this, right? Now, if I want to find the area under this curve, let's say between t equal to 0 up to, like, let's say t equal to 4 seconds, if I want to find that area, well, that's not so easy to do by just breaking it into triangles, right? Probably a lot easier that we just integrate from 0 to 4, 10, like this, right? And this would be 5t squared, right? From 0 to 4. Did I do that right? See, yeah. And so this would be 5 times 16, which is 80, right? So the only reason I did this step here was just to say that finding the area under the curve is equivalent to finding the displacement. And then we said, well, to find the area under this curve, we could just use the trapezoid formula. But sometimes you can't do that, right? Sometimes it's a curve, in which case you actually have to do this. So does that answer your question? The distinguish between the two of them?
Yeah.
That's a really good question, because I totally skipped over that, so I apologize. I just said area under the curve, and then I just started doing this so I could see. Yeah. All right, any other questions before we go on to the next problem? All right. Didn't even use these. We could have, though. If you want to, you can use these equations. You will get the exact same answer. I promise. It will work. All right, so bring those equations down here, and now we'll do kind of a pretty basic problem. For this, I'm going to kind of show you the way that I do these problems. You do not have to do it this way, but if you want to give it a shot, I promise you this method will be pretty good. Okay, so this says a car accelerates at 5 feet per second squared. So I'm going to make a little table here where I write down 5 feet per second squared for 1,000 feet. Okay, well, that's going to be the displacement, right? 1,000 feet. and has a final velocity of 90 miles an hour. So that's our final velocity. And instead of writing mph, I'll just write miles per hour. Our goal is to find the initial velocity in feet per second and in miles per hour. So we're given these 4 pieces of information. Well, 3 pieces of information and 1 unknown, which is the initial velocity. So I like to just make a little table, and then I use my table, and I inspect all of these equations over here, and try to figure out what the right equation is going to be. So again, for me, the way I do this is say there's one variable missing from these pieces here, right? What is that variable? Of our 5 variables that we could have. What variable is missing? Time, right? So all we need to do is just like go through here and find the ones that there's a time, that's not going to work, there's a time, there's a time. Oh look, this one doesn't have time in it, so we'll just pick this one. So we know the equation we want to use is going to be v final squared is equal to v initial squared plus 2a delta x. However, we have one problem, which is that the feet per second squared and the feet here are not the same units as miles per hour. So we do need to convert the miles per hour over into feet per second. So let's do that over here. So 90 miles per hour. Anyone know how many feet are there in a mile? So the way I do this is you just put mile down here and you put feet up here and you just ask, how many feet are in a mile? 1 mile is how many feet? Okay, some are saying we can multiply by 1.467. That probably works too. Is that going to go from miles to hour to feet per second, basically? Yeah. Yeah, we're gonna do it step by step though. 5280. That's right. Okay, there's 5,280 feet in a mile. You don't know off the top of your head. That's fine. It's something you can look up. Your textbook has a list of all of these things. And we also need to get rid of the hour right here. So in the numerator right here, we're going to put an hour. And we need to convert that hour into seconds because our goal is to get to feet per second, and this will do that. So 3,600, yeah, 60 times 60, right? 60 minutes and 60 seconds. So multiply all those together, that should give us an answer for what our initial velocity is. I'll just say this is, or final velocity, sorry. This is VF. So what does that give us? VF. So you're saying 1.4. I'm assuming, Summer, that if you take 5280 and you divide by 3,600, you're probably going to get 1.467, right? Is that what's going to happen? That's probably what happens. Let's just see. 5280 divide 3600. Yep, it's 1.4. Oh, it's actually 1.46 repeating, right? So that's interesting. That makes it something that's kind of easy to remember. Maybe, I don't know. Times 90, I get 132 feet per second. Okay, so that's our final velocity. Oh, I made a mistake here. This is supposed to be squared. So sorry about that. It's VF squared equals V initial squared plus 2a delta x. And that's the symbol we're solving for, so we'll just solve for it by isolating it. So VF squared minus 2a delta x goes on the left side. On the right-hand side, we have V initial squared. But what we'll do to get rid of that is we'll square root both sides. This, keeping in mind that this is going to give us a plus or minus sign over here on the left-hand side. So our answer is going to be plus or minus the square root of VF. Oh, that's this now, 132. Whole squared. Minus 2 times the acceleration, which was 5. Minus 2 times 1,000 feet. And what do you get? Did anyone solve this during the break? It's okay if you didn't. This should be equal to V initial. So V initial should be equal to plus or minus whatever you get from all of that. Did anyone get an answer? If so, you can write it in the chat. If not, you can try to beat me to calculating it. 86. Okay. That's also what I got. I got 86.2. We'll write down 86.2. And the unit is going to be feet per second. Now we have to decide, do we take the positive or the negative one of this? And since we don't know how long this car has been moving, we probably want to just assume that it's been accelerating forwards the entire time and take the positive answer here. However, the negative answer would also work, but it's more likely in this case that the positive answer is the right answer. But it isn't clear. It's not 100% clear. However, if you think about the way a car works, cars don't tend to start going left and then always accelerate to the right so that they turn around, right? Normally cars are just moving in one direction, right? You start off at 86 feet per second, you accelerate up to whatever, 90 miles an hour in this case. We can also convert this into miles an hour by doing the opposite of what we did before, which I assume is going to be by dividing by 1.66666667 or whatever, or 1.46, right? Or 67. And that gives us 58.7 miles an hour is what I got. Those are our answers. Anyone have any questions? Pretty easy problem. We're gonna ramp the difficulty up almost immediately here. Start doing problems that are quite tricky. Okay, I'll do this one. Actually, this one isn't super tricky, but the next one is. All right. Miles per hour? That's what I got. Did anyone else get the same answer? 58.7. Leave it up there. Let me know if you got the same answer. And then what I would like you to do, we got a little bit of time. I want you to take, what can we do? I'd like to do at least 2 more problems. Take 3 minutes, read this problem, and try to set it up. And then while you're doing that, I'm gonna draw a picture of what we got going on here. But read the problem and try to set it up. Ball is thrown vertically from the top of the cliff. Find the initial velocity if 5 seconds later it's 200 feet below or 500 feet below. Okay, I think that's enough time to at least get acquainted with what's going on here. So we have a ball. It's thrown from the top of a cliff. Maybe there's a little dude down here who's throwing this ball. He throws the ball upwards at an unknown speed. We're trying to calculate what the speed is. We're just going to call it initial velocity. And all we know is that the ball goes up. And of course, due to gravity, it eventually has to start coming back down again. We're going to assume it's only traveling in one dimension. So it's thrown straight up and then it goes straight down. It gets to this position where it's now moving downwards with subspeed. We don't know what it is. But we know that 5 seconds have elapsed. And we know that it's 200 feet below the cliff. Oh yeah, I was going to move it down. So we have more room to draw on this thing. So it's down here now. Okay, so we need to figure out what was its initial velocity if 5 seconds after it's released or thrown, that it is 200 feet below the cliff. And I guess potentially the velocity could have been up or down, but we'll start with the assumption that it's up for now. All right, so how do we do these problems? So as I said before, what you want to do is you want to use some symbols to represent what's going on in the problem. So the 5 variables, the 5 symbols we have are these right here. We've got change in position. I'm going to write delta y here because it's going up and down. We've got acceleration, we've got initial velocity, final velocity, and time, right? And in order to even use these equations, we need to define an axis. So I'm going to call this the positive x direction. No, positive y, my bad. Positive y direction. So down is going to be negative. And I'm also going to say you need to pick a coordinate that's y equal to 0. So let's define this point right here to be y equal to 0, the starting point. Okay? Let's go through and let's fill out all of these pieces of information here. So what do we know? What's the time interval? It starts at t equal to 0. It ends at 5 seconds. The time interval is 5 seconds. We do not know the final velocity. We do not know the initial velocity, which means we must know these top 2, or else we won't be able to solve this problem. What's the acceleration going to be in this problem? Okay, it's g. Now, in this problem, everything is written in feet, right? So what we're going to use is g equal to 32 feet per second squared. And in this case, that's going to be pointing downwards. So negative 32 feet per second squared. That's our, and it's negative because gravity pulls downwards while we made up positive. We could have made down positive too if we wanted to. It may have made the problem easier. Okay, and then we have delta. What was there a question? I thought I heard someone queuing their mic. All right, delta y.
How did you get? Sorry. How'd you get 32? I'm confused.
Gravity accelerates at about a rate of 32 feet per second squared.
Oh yeah, my bad. I thought it was 9.8 meters per second, so I confused the units. My bad.
That's okay. 9.8 meters is about 32 feet. All right.
Yeah, I understand.
That's okay. Delta y. So this is the part that's going to be a little tricky, and you will probably make mistakes on this one. So be careful with this one. What should my delta y be in this case? Oh shoot! Is my head covering? No, that's fine. What's delta y going to be? 300? We don't know how tall the cliff is, by the way. That's why I made y equal to 0 at the top. 200, so we should just put in 200. Negative 200? Well, how do we know? Is it positive or is it negative? It starts from 0 and it goes to 200, right? So your y initial, what is y initial equal to?
0.
And what's y final equal to?
200.
No. If up is positive, then y final has to be negative 200. Which means delta y is negative 200. Now, how do I know that? How do I know it's negative? Well, it's because of two things. One, I made positive y up. And if positive y is up, then that means negative y is down, right? So the y coordinate of this point right here, y final, has to be negative 200. Now, I know that's not obvious, but one thing I'll say is that if you make up positive, if an object starts from a high elevation and it goes downwards, its displacement will be negative. If it starts from a low elevation and it goes up, its displacement will be positive. So think about it like this. If you're going up a hill, what's happening to your elevation? It's increasing, right? If you're traveling up a hill, your elevation increases. If you're going down a hill, your elevation decreases. So when you go up, delta y is positive. When you go down, delta y is negative. That is assuming that you're defining up positive, which you don't have to do. But in this problem, with up positive, initial position is 0, final position is negative 1, negative 200. And you got to get that right. If you don't get it right, then you will always get the wrong answer. But so take your time in the setup, just like with the previous problems with the equilibrium problems. Getting all the forces was really important. The setup is important. The picture is important. Your axes are important. What you call positive, important. So now, once we have all this information, it is very easy to solve the problem. Our initial velocity is here. That's the thing we're trying to find. We're given delta y, a, and delta t. So we need the equation that does not have final velocity in it, which I would argue is this equation right here. One that we are going to be using a lot. So rewriting it here, what we have is delta x should be equal to, I'm going to drop all of the vector signs because it becomes very time consuming to write them. V initial times t plus 1 half at squared. Same thing here. I'm dropping the delta t's from the t's. Just writing it at t because it starts at t equal to 0. Yep, we need to solve for initial velocity. So I would prefer that you don't plug in your numbers first. Instead, what you want to do is solve for this. So what do we get? We'll get delta x minus 1 half at squared is equal to v initial times t. We divide the t to the left-hand side, so we get delta x minus 1 half at squared divided by t should be equal to v initial. So plugging in the information we have, delta x negative 200. So you wait till the very end, and you plug all the numbers in with their units. Minus 1 half. Acceleration should be negative 32. Don't get confused by the fact that there's a negative sign here. You still need to make the acceleration negative, because that negative came from algebra. Right? It was originally a plus, we moved to the left. So you still need that negative sign and this negative sign. Times t squared. Our time is 5 seconds. And then we divide by 5 seconds. That should give us our answer for our initial velocity. In fact, now we should be able to figure out if we were right or wrong about it being positive. Because there's only one solution here, and it's either going to be a positive number or a negative number. If it's negative, the rock must have been thrown downwards. Does that make sense? You get 40? Thank you, Summer. So I'm assuming if you get 40, these numbers must work out really well. 1 half of 32 is 16. 16 times 25 is 250 plus 150 is 400. So this whole thing is 400. It's positive. 400 minus 200 is 200. 200 divided by 5 is, yeah, it's 40. Okay. Almost all these problems that come from that packet have really nice round numbers. There's our initial velocity. And it's positive. So in fact, it is going upwards. It was going upwards. Have we got a negative number? Well, then it must have been thrown downwards. All right. Anyone have any questions? part A. Yeah, do the same thing for the second part. Let's use green. Now, luckily for the second part, we only need to change one number, right? We only need to change, because the second part says 500 feet below the edge of the cliff, so we only really need to change one thing. So let's do that. We'll make it green. And we'll just change the 200 to a 500. Not like that. Oops. 500. And this will probably give us a negative answer now, right? All right, let's see here. Quick question. Whenever we solve the problems, can we use the formulas that we've made, or we need to derive the formula? No, you can just use the formulas. You don't need to derive them. Summer says you got negative 20 for part B. Yeah, negative 20, I agree. Yeah, so this tells us that it was thrown downwards. Okay, so if 5 seconds later it's 500 feet below the cliff, hopefully it makes sense that you would have to throw it down for that to happen. Because only 5 seconds have elapsed, so it must be going straight down. Not must be, but the math kind of bears that out. So this means that it was actually thrown downwards. Okay, there's a very straightforward kinematics problem involving free fall. And let's see if we can do one more. Let's see if we can do one more. Let's do... Let's do one that has two things moving at the same time, because I think that will be the most useful to you in your homework. And I think we're going to have to put this on a second notebook. So let's do that. And this will be the notes for next time, but we'll start with this one, because I have a feeling we won't finish this today. Got a feeling we won't finish this today. So same thing as before. Take like 2 minutes to read this problem, and see if you can't draw your own diagram while I'm drawing a diagram here too. Yeah, we have two things moving now, so things get kind of tricky. Okay, that was about 3 minutes. Maybe 4, actually. Yeah, we've got like 18 minutes left. We can totally solve this problem in 18 minutes. Okay, this is our picture. Ball A is thrown upwards at 10 feet per second. So ball A is red, and it is given an initial velocity of 10 feet per second up. From the top of a building that's 100 feet tall. So here's our building. It's just a square thing, and it's 100 feet tall. Rectangle. And it misses the edge of the building on the way down. So it's thrown up, and then it's allowed to fall. And I'm drawing it as if it's kind of going in a parabola, but really it's going straight up and straight down, okay? I'm doing this just so that they can hit each other. But it's thrown straight up, and it falls straight down. At the exact same moment, okay, the same time that A leaves the top, B leaves the bottom, is thrown upwards at 60 feet per second. That was really fast, Summer, if you already solved it. Let's see if that's right. At the same instant, ball B is thrown upwards at 60 feet per second from the ground. We want to find where and when do they meet, or do they hit the ground first? There's 2 possibilities. One possibility is that ball A goes up, and it starts to fall down, and by the time it gets to here, B is still on the way up, and they cross paths at some point, let's say. Let's say they cross paths at some point right there. Or ball A falls all the way to the ground, and B has already gone up and down during that time period. It's one of the 2 possibilities. What we're going to do is we're going to assume that the balls meet, okay? And if our assumption is wrong, then something with the math will go bad. We'll get some kind of square root of a negative, or we'll get 0 equals 0, or something bad will happen with the math if, in fact, they don't meet. And I'll show you how that could have happened when we get to the end. But let's assume they meet first, because I think that's the best thing to do. All right. So this is a problem in which we're given much less information than we have in the previous problems, right? So in the previous problems, we were given a time, a velocity, and we also knew the acceleration, because just as in the previous problems, the acceleration in this problem is going to be 32 feet per second squared. So we know that, but all we know for each ball is kind of like where they start. This one starts on the ground. The ball A starts on the top of the roof. We do not know anything else. So if we were to create a little table, one table for ball A, and then another table for ball B, and write out an information, it'd be pretty clear that we're missing some information. But we're still going to write them out anyway because we don't know what else to do. So, step 1, draw a picture. Step 2, pick a set of a coordinate system, okay? So, we'll do the same coordinate system we did before. We're going to make the up direction to be positive y. We also need to pick an origin. What do y'all want to pick for the origin? Do you want to use the ground, or do you want to use the top of the roof? I promise you it makes absolutely no difference. You get the same answer either way. Ground. Okay, let's use the ground. 2 people said ground, 1 people said top. You can try it both ways. I promise you will get the same answer. So this is y equal to 0 down here, and positive y is going to be up. Now, we're going to write out all of our information for each of these objects. So what is that information going to be? It's going to be things like the initial velocity of the ball, which, because there's 2 balls now, I'm going to use different variables. We're going to say v naught A and vf, v final for A. They'll both have the same acceleration. We can go ahead and throw that in here. Since we're making up positive, the acceleration will be negative 32, because the acceleration of gravity is downwards. We can put that in for both of them. I'll make all these blue here in a second on this side. So we'll also have an initial velocity for ball B, and we'll have a final velocity for ball B. The initial velocity for ball A is given. It's 10 feet per second. And the initial velocity for ball B is also given. It's 60 feet per second. They're both positive. The other piece of information we can have is time. Now, we don't know what the time is in this case, but we do know they start moving at the same time, which is kind of helpful. And finally, what we would need is delta x. Now, because delta x is represented by doing x final minus x initial, what I'm going to do is I'm going to say that we'll write it like this. X final for A will be one thing, and X initial for A will be another thing. So we'll kind of break it down into 6 variables now. We'll make the final position for each of them be our other variables. And I'm doing that for reasons that will become very clear as we do the problem. We don't know the final positions, but we do know the initial positions. That's the reason I'm doing this. The final positions are going to be an unknown. You want to use delta y? Yeah, we can use delta y. That's fine. That's probably what we should use since I gave you a y coordinate. Sorry about that. Thank you for pointing that out. All right, so this is going to be y final for A, y initial for A, y final for B, and y initial for B. So let's fill out what we know, and let's make all these over here blue. So we don't know time. What's y initial for A equal to? We picked y equal to 0 to be the ground, right? So what's y initial for A going to be? 100 feet, right? It starts right here at a y coordinate that is 100 feet up at the ground. So y initial for A is 100 feet. What's y initial for B? 0, right? Okay. Now, before I say anything else, I just want to check with everyone. Is there any other information that I'm missing? Or did I already write down all of our information? Do we know the final velocities? We don't, right? We don't know what the final velocities are. The final point, by the way, is going to be when the balls meet. So we have no information about these. So I'll just put in here that this is a question mark. Do we know the time? We don't know the time. That's one of the things that we're trying to figure out, right? When do they meet? And where do they meet? Do we know anything about the relationship between these things? If they do in fact meet, what would be true about this time and this time over here? Would they be the same time? They are. Okay, so we don't need to write, and I didn't do it, we don't need to write a different variable for the time in both cases. The time should be the same in both cases. Now that's handy, right? Now what about this? What about the final position of ball A and the final position of ball B? Are those related to each other at all? They're also the same, exactly. So how about, just to keep things simple, instead of writing all these silly variables here, let's just do y final for both of them. We could just do y, actually, if we want to. We could define it as y to completely not have to write all these variables. That's okay. We know these are the same, because that's the point where they meet. So we basically have just defined something. We've just defined this point where they meet to be y final, right? And that is one of the things that we're going to calculate. It might not be the first thing we calculate, but we know they're the same. We just don't know what they are, okay? So how do you proceed if you're missing all this information? So just to be clear here, we have too many unknowns. We have 3 pieces of information, 1, 2, 3, but it's really more like 2.5 because you need delta y. In fact, I'll just show you the equation. The primary equation we're going to use to solve for this is going to be this one. And you notice that we have acceleration and we have initial velocity, but we only have part of delta y. So we don't have enough information to find time. Is that clear to everyone? There's not enough information to solve for time because we don't really know what this is, right? So does anyone have any recommendations on how we solve the problem then? How can we solve the problem?
Should we use what we have to solve one equation, and from there we get more of our A's and T's, and then from there we get another equation?
All right. Set 2 equations are the same. That's right, Chris. I think that's similar to what you were just saying. So let's try that. So now we don't know enough information, but we can write equations down, right? So let's write an equation down for A. For A, what we're going to have is y final minus y initial for A. That's the delta y. This should be equal to v initial for A times the time plus 1/2 at squared. And then we could write that exact same equation for B by just copy pasting this one, making it blue, and just replacing all of these. So this will get replaced, and that'll get replaced with the B. Because they are, in fact, the exact same equation. We just need to put in different numbers. All right. So let's start plugging in our numbers. So y final, that's a variable. We don't know what it is, so we leave it alone. Y initial A, though, is 100 feet. Right? And this is equal to V initial A, which was 10, times T, which is an unknown. And then we're going to have a minus 1/2 32. And you know what? That's probably confusing. We'll do negative 32 inside of here so that it's clear. And then a T squared. And then we just go and do the exact same thing over here for this one. Probably going to run into the... Move up. We'll go up a little bit for this one so we don't run into the chat. For blue, or for the ball blue, the ball B, y final is still an unknown. Here, let's box this off. That's our information. Y final minus 0, because that was its initial position, is equal to V initial B, which is 60, times T plus 1/2 of negative 32 feet per second squared. I'm running out of room here. That's okay, though, because the next line will be shorter. So we get that. And now let's do some simplifications. We know that both of these have the same variable yf and t. So what we could do is we could just, do exactly what someone had said. So yf then is going to be equal to all the stuff on the right-hand side plus 100. So we'll have 100 feet plus 10 feet per second times t. And we'll simplify this a little bit. 1/2 of negative 32 would be negative 16. We don't have much work to do on this equation up here because it's really just this 0. So this becomes y final. Whoops. Clicked on that, but it didn't do it. Y final is equal to 60 feet per second times t. And yeah, that's what we'll do somewhere. We'll set them equal to each other. And then we have minus 16. And now all we need to do is to set these two equations equal to each other, because they're both equal to yf. So let's do that. When we make them equal to each other, we get this. 100 feet plus 10 feet per second. We could also subtract the equations if you wanted to. Times t minus 16 per second squared. This t squared is equal to 60 feet per second times t minus 16 feet per second squared times t squared. Now what's really interesting here is that, I think it's interesting, I don't know what's that interesting. This piece cancels out in both equations, because they're both affected by gravity in the same way. It's almost like gravity doesn't matter in a weird way, because they're both affected, they're both being slowed down in the same way. So we end up with a pretty simple equation that we can solve, which is, let's get all the terms on the same side with each other. So the left-hand side, we'll just leave 100 feet right here. And on the right-hand side, we'll group some terms. We have 60 feet t minus 10 feet t, so that's going to be 50 t. And that means that t is equal to 2 seconds. Now, let's just think for a second. What would have given us a silly answer? Can anyone tell me? They do meet, by the way. They meet at 2 seconds. But what could we have changed to make it so that we didn't get an answer that was reasonable? Maybe so that we got like a negative answer or something like that. What would have happened? Let's go back to our picture and let's think about this. So that, Andrew, that would not have changed it. Y equal to 0 at the top would not change it. that you get the same answer no matter what. The ball A was thrown at 10 feet per second, right? And ball B was thrown at 60 feet per second. What if we made this just really simple? What if ball B had only been thrown at 10 feet per second? They probably wouldn't meet, right? Would you all agree? If this was 10, they're probably not going to meet at that point, right? So what happens to our answer? Well, if this was also 10 feet per second, right? You'd get 100 feet equal to 0, and that's just silly, right? So that's what I mean, that if you change the numbers around a little bit, you start to see what would actually make these things become unreasonable. Yeah. But it turns out that if you picked 20 feet per second, then we would have done 20 minus 10. This would have been 10. 100 over 10 seconds. There actually would have been an answer. Okay, but yeah. Okay, so that was only half the problem. The other half of the problem was to calculate where do they meet. Now, this is important. Where they meet is important. Because now if they meet below the ground, well, that's a problem, right? So let's see. So you have to actually solve both. To figure out where they meet, let's just use this equation right here. It's the simplest equation to use. So the final position where they meet, y final, should be equal to 60 feet per second times 2 seconds minus 16 feet per second squared times 2 seconds squared. So if they're the same speed, the answer would just be they don't meet at all. Yeah, Chris, it would be that they both hit the ground before they meet. Yeah. What do you, 56? Now, so the two things that have to happen here are not only that you get a positive answer right here, but this number has to be between 0 and 100, basically. Or greater than 0, I would say. Because I think if you put in 20, see, 20 times 10 would be 40 minus 16 times 100. Yeah, it'd be below the ground. So if you made it so that this was 20 feet per second, what would happen is that your answer for the first part would be 10, but your answer for the second part would be negative. So then they would hit the ground first, basically. Okay. So does everyone agree that you get 56 feet? 120 minus 64. Yeah, that sounds right. Okay, great. We're at 5:09. I don't want to keep you all any longer. If y final had been negative, Summer, then that would mean that they would hit the ground before they meet each other. Okay, that's what it would mean. So they basically would both hit the ground before they meet each other. All right, stopping right there. And yeah, we'll continue next time. We're going to do some more of these problems. If you want to look ahead, you can go to Canvas and you can look at this document here, the Physics 1A examples packet, and you can look ahead to the problems we're going to do if you want to do them before class. I think often it helps a lot. So where are we? Well, keep going through the document. Again, this is on Canvas. There's equilibrium. We did that. There's rotational equilibrium. We did that. So where are we? We're on kinematics. And the first problem we do tomorrow will be this flower pot problem, number 6. So if you want, that was a tricky problem right there. And then we're going to do another 2 balls meeting problem, and then we're going to do this one. I would recommend looking at the flower problem and taking a look at number 10. And I'll give you time in class as well, but number 10 is pretty tricky. Pretty tricky. Okay, so that's it for today. I hope everyone has a nice evening, and I'll see you on Wednesday night, or Wednesday afternoon. Where's OBS?